In this problem, we have a trail going from a campground up to a scenic overlook, and we're told that the campground is at an elevation of 8,000 feet and the overlook is at an elevation of 11,100 feet, and the length of the trail is 14,100 feet. And we're asked to find the angle of elevation of the trail. So I draw a picture here. So we're going up. Let's say the campground is here. Let's call it CG. And the overlook is here. And this trail is 14,100 feet. Of course, we're assuming that's relatively flat, not up, down, just to make the problem simple. And so there's probably a hill back here also, but this elevation is 8,000 feet. So let's measure from the horizontal. This is at 8,000 feet, and the overlook is at 11,100 feet. And we're asked to find the angle of elevation. So measuring from the horizontal, if we were looking up at the overlook, that's the angle of elevation. So let's let theta equal the angle of elevation. And we have a right triangle here. So the change in the elevations will be the length of this side of the triangle. So 11,100 minus 8,000 is 3,100 feet. So from theta, this will be the opposite and the hypotenuse. So this implies that the sine of theta equals 3,100 over 14,100. Of course, these zeros cancel, so we can just use 31 over 141. Okay, so now this obviously isn't the output for a special angle theta, so we're going to use our calculator. This implies theta is the sine inverse of 31 over 141. Make sure your mode is in degrees. Sine inverse of 31 divided by 141 is approximately, we'll round to the nearest tenth, 12.7 degrees. Whoops. So the angle of elevation is approximately 12, whoops, my decimal in the wrong spot, 12.7 degrees. In the next problem, we're going to use bearings, and bearings are, like I say here, they're a method of giving directions by stating the acute angle measurement and the direction from due south or due north. So I have three examples here. The first letter stands for north or south. This is always north or south. Then you'll have an acute angle, and then this tells you which direction to measure that angle to. So that you can draw a north-south line anywhere. Say we're standing here. If we're looking north 35 degrees east, we're looking north and then measure 35 degrees to the east. Okay, so this would be north 35 degrees east. South 55 degrees east, we'd be looking south and then measure 55 degrees. Maybe a little farther than that. This would be our 55 degrees. So this would be south 55 degrees east. So always from the north-south line. Wherever you're at, now I'm over here, that's where you're going to draw your north-south line. So south 42 degrees west, we'd measure 42 degrees to the west. So this would be nautical bearings, usually. There are also bearings that, that are used in flight that are a little different than this. This is usually what I will use, but in your homework you might sometimes see bearings that are used in aviation, I should say. And those are always measured from the north line. So in aviation, you might see like north 260 degrees, and you're always, I'm not sure exactly how they write that, but you always, in aviation, so notice this doesn't have to be acute, always measure from the north line, and then you go in a clockwise direction. So this would be, it's kind of awkward because we're used to starting from here, right, and going the other direction, but so this would be 270, excuse me. So it's a little bit short of that. Okay, I won't test you on that, but if it comes up in your homework, I just want to mention it because I think there is a problem later on that might involve that. Not in this section, however. This section, we only are going to work with these. I'm more familiar with using these types of bearings. This is the first textbook I've used that had the type that's used in aviation. Well, some of you maybe know more about aviation than I do. All right, so this problem deals with ships, so we use nautical bearings. Even when we do some flight problems later, I'm still going to use this type of bearings. Okay, so two ships leave port at the same time. One ship sailing in the direction north 27 degrees east at a speed of 12 miles per hour, and the second sailing in the direction of south 63 degrees east at 15 miles per hour. So we're going to approximate the bearing from the second ship to the first ship after 1 hour. Okay, so let's draw a picture first. That's most important. So here's our port, and then one ship leaves sailing north 27 degrees east. So let's draw our north-south line. So 27 degrees to the east, maybe about like that. And that's 12 miles per hour that ship is going. Let's just call this S1 for ship 1. The second ship is south 63 degrees east. So, and this one's going faster, so I'm going to draw the line a little bit longer. This is 63 degrees east. Approximate the bearing from the second ship to the first ship. So here's the second ship. Okay, so what that means is from this ship, you need to draw a new north-south line. Then look at ship 1, and we need to find this angle right here. Then the bearing will be north theta, however many degrees theta is, west. So we need to find theta. Use north theta west. And I assuming my drawing is correct, accurate here, but this one's going faster, so I know this is longer than this. Okay, so what we can use here is the fact that this angle, I'm going to erase this T, it's in my way, we'll just use P for port, would be, well, notice this is a straight angle, 180 degrees, minus 63 degrees minus 27 degrees, and these two add up to 90 degrees, so the degrees here. So we do have a right triangle. The other thing we know is how fast these are going, and we want to know the bearing after 1 hour. So in 1 hour, the first ship is 12 miles away, and the second ship is 15 miles away, right? It's going 15 miles per hour. All right, well, how are we going to find theta? This is the tricky part. Well, we need to use this angle here. Find this, we need to use this triangle, right? So we need to find this angle right here, and then we can figure out what theta is. So a couple things we need from geometry here is the fact that these are parallel lines. So when you take this line here, we know that alternate interior angles are equal. So in other words, this angle and this angle have the same measure. This is 63 degrees. So if we can find this angle, we can subtract to find theta. Okay, and then we can, so sorry, lost my train of thought for a second. Let's let's give this a different name. Let's call this alpha. So note theta equals 63 degrees minus alpha. Okay, so we need to find alpha. Well, from the point of view of alpha, we know these two sides, that's opposite over adjacent. So this implies that, this triangle implies that the tangent of alpha is 12/15, which we could reduce to they're both divisible by 3, 4/5. And so we'll use tangent inverse. Again, this is not an output for one of the special angles. So tangent inverse of 4/5 is approximately 38.7 degrees. So theta is approximately 63 degrees minus 38.7 degrees, which is 24.3 degrees. So the bearing from the first, or from the second ship to the first is north 24.2 degrees west. Okay, so that brings us to our last type of problem in this section, which is simple harmonic motion. I think I'm going to take a break here and I'll do that in the third video.